Hello everyone, I am Saahas Bhardwaj and I'm a faculty at the University of Alabama. I did my PhD at Purdue University and then I worked as a postdoctoral researcher at Purdue for a year and a half. I was involved with this project during my stay there as a postdoctoral researcher. I'm going to present the part that talks about vent holes, which is module 5 for this series of presentations. And I'm going to talk about why did we feel that there was a need for this topic to be addressed, and what is the current research that we've done and the progress that we've made on the topic of vent holes. In this module, I'm going to talk about the methodology that we've developed, the assumptions and input parameters that go into that methodology, and then I'll talk briefly about the proposed equation and use that equation to solve an example case of a typical wall and come up with detailing requirements for vent holes. I'm also going to talk briefly about the important factors that need to be considered, the water cement ratio, and then based on our studies, what are the minimum requirements we believe that need to be provided. But before I get into all of this discussion, let me talk briefly about why this topic is important. When we start talking about composite walls, we are talking about a significant volume of concrete which is kind of sealed by steel plates on all sides. And there is a need of providing outlets for pressurized steam which would build up in all that volume of concrete as the temperatures start heating up. And this was something that we had observed in our experiments, the buildup of that pressure and the steam venting out at high pressures. And in some cases, we also observed the kettle-like sound that comes once you have steam building up in the system. So all of these observations made us look into the provisions for detailing requirements for vent holes. So we wanted to come with detailing requirements for vent holes. And what I'm going to talk about is the assumptions that we've made in developing these requirements. The first assumption that we made was that all of the water in concrete, be it the free water or the chemically bonded water, is evaporable. And for our case, for our specimens, that water percentage was 16%. And this assumption is primarily based on what we had observed from our specimens. So after we had tested our specimens and subjected them to standard fire curves, what we cored concrete out, and what we observed was that the cores were highly disintegrated, and we felt that it was reasonable to assume that you would lose all of the water in concrete under these circumstances. And then the next assumption we made was that the vent hole calculation we are making is for a steady state where the amount of vapor generated due to the fire loading is equal to the discharge rate that would be based on the vent holes provided. But before this equilibrium is achieved, there is a pressure buildup which the method allows to be considered. And that is an input parameters that the designers can consider. And for our case, we considered that pressure buildup to correspond to a maximum concrete pour height of 10 meters, and which, based on previous studies we've observed, does not significantly degrade the compression capacity or the compression behavior of the walls. So based on these assumptions, the input parameters are You can start off assuming one of the things. You can start off assuming the vent hole spacing or the size, and then come up as an output, you will get the other. If you assume the spacing, then you can get the size. The other input parameter would be your vapor generation rate, which would depend on your section thickness. And then, if you know the surface temperature curves, you can you can calculate the evolution of temperatures through the cross section and then calculate the vapor generation rate. And again, the set pressure is something that the designers have the freedom to decide. But again, for our cases or for our studies, we've considered that to be the pressure corresponding to a concrete pour height of 10 meters. This schematic shows how this method works. So what we're looking at here is a cross section of the composite walls, where we've got the face plates, the concrete infill, and then we are showing the moisture content of concrete as blue bubbles in there. And what we're considering is that you have the moisture in there, and as you start applying the fire load, and that fire load starts increasing the temperature of concrete, your free water and then also the chemically bonded water, depending on what the temperature of concrete is, starts converting into steam. And that would start increasing the pressure inside the wall. And then the vent holes would start discharging vapors. And what we are considering in this method is that once you have reached a certain set pressure, the pressure that we are comfortable to let develop in the wall, at that instant, the rate of vapor produced is equal to the rate of vapor discharge. And then we use the proposed equation to calculate what is the detailing of the vent holes required to establish that equilibrium. Based on the assumptions that we've talked about previously, we can use this proposed equation to determine the size of required vent holes or the spacings of required vent holes. And there's a lot of parameters, and all of them have been defined here. But the important ones, let me talk briefly about the important ones. The discharge rate M, which in our case would be equal to the maximum rate of uh, vapor production, and then the area of the hole, which would be one of which can be your input parameter or your output parameter. Um, so you can choose between the area or the spacing. And then the set pressure is again something the designer can control. And just to repeat, we've considered that as the concrete casting pressure corresponding to concrete pour height of 10 meters. And then there's some standard values, the specific heat ratio, the ideal gas constant, and molar weight and discharge coefficient um, that we've considered. Now, this slide presents the steps involved in using this equation to calculate the size of the vent holes or the spacing of the vent holes. Let's go with the case where we use the vent hole spacing as an input parameter and then come up with the diameter or the size of the vent hole required. The first step would be you would consider what is the maximum allowable pressure, what is the pressure you are okay to let develop in the wall, and that is the set pressure P. And since you know the vent hole spacing, that's an input parameter. Let's say I decide that I want to provide vent holes every 12 feet along the length and the height of the wall. Then I can calculate the tributary area for a single vent hole, which is the amount of concrete that would contribute its vapor to that vent hole. And then based on that tributary area and the thermal gradients through the cross section of the concrete, I can calculate the rate of vapor generation. Um, so I would basically get the thermal gradients through the cross section, and then as the temperature of concrete through the cross section starts increasing, I can calculate the rate of vapor generation at different times. Once I have all of these parameters, I can use the equation to find out what is the size of vent hole or the diameter that I need to maintain the internal pressure below that set pressure. Here what we presented is a schematic which shows what would be the effective area for a single vent hole. So that is the amount of concrete that would contribute its vapors to that vent hole, and that again is a function of the spacing of the vent holes. Let us use this vent hole size calculation for an example. What we're considering is a typical composite wall, the 600 thick wall, and we considered the water content to be the same as it was for our specimen, 16%, which is on the higher end, but that's conservative. And what you would need to use this method is the duration, the amount of time that different thicknesses through the cross section of the wall take to get to a temperature above 100 degrees C. And you can look at the rate of vapor generation. So through the different locations, there is a time, and then you can calculate the rate of vapor generation based on the water content that was in that region, which is above 100 C, and the time taken for that region of water to go above 100 C. And then what we do is we pick up the maximum rate of vapor generation, and then you calculate what your set pressure is. And what we're doing is we are considering three different set pressures and then different spacings of the vent holes. And on the curve you can see there is a set pressure of 0.0088, which corresponds to a concrete pour height of 9 meters, and then there's a set pressure which is half of that, and then there's a set pressure which is twice of that. And depending on what your effective area is, which is controlled by the spacing of your vent holes. Let's say your spacing of the vent holes is 1 meter by 1 meter, which means your effective area for a vent hole is 1 meter square. You would need a vent hole diameter for around 7.5 millimeters. However, if you were to increase your effective area to 3 meters square, let's say you had a vent hole grid of 3 meters by 1 meter, where the effective area of each vent hole is 3 meters square, you would need to provide a vent hole diameter which is around 12 or 13 millimeter. So your vent hole diameters could increase significantly as you keep on increasing the effective area. One of the parameters that we may need to consider in the design of vent holes is the variation with a change in the water cement ratio. So the figure shows that the vent hole diameter requirements do not change significantly with the change in water cement ratio, because the water cement ratio has a minor influence on the pressure buildup inside the concrete. So we've used the methodology that I just described to conduct various parametric studies and come up with a set of minimum requirements that would work for all those sets of parameters. We've considered walls with different thicknesses, walls with um, different water cement ratios, and what we've concluded from our studies is that, and that's what we are recommending, that the vent holes need to be spaced. The maximum spacing can be 3 to 3.5 meters, both longitudinally along the length and then along the height. And we're also recommending that the diameter, the minimum diameter of vent holes be 1 inch. And just to give an example, we've put in a table which shows some of the cases that we've considered. So let me explain this table. So we are considering two allowable pressures, 10 psi and 15 psi, two water contents, 14% and 16%, and then we are considering a minimum recommended diameter, which is 25 mm. And what we're calculating is for different walls, walls with no fire protection, and then walls with different thicknesses of fire protection, 3/8 of an inch, half an inch, 5/8 inch, and 3/4 inch. What is the effective area, the maximum effective area that you can provide? So your effective area needs to be less than this. And again, to go back, this effective area is related to the spacing of the tile. So if I have a higher effective area, which means the spacing is more, but if I have a lower effective area requirement, which means I need to space the space the vent holes closer. So what we can see here is that if you're meeting the minimum requirement and you're providing vent holes at 3 meters apart, which means the effective area would be 9 meters square. So for walls with fire protection, that is considerably conservative from what, as compared to the calculations we have here. And even for walls with no fire protection, that is conservative in most cases. However, if there is a change in parameters, if we want to consider an allowable pressure significantly higher or significantly lower than what we've considered, then we may have to go back and look at the equation and calculate if the minimum requirements will still satisfy.